Welcome everybody to section 4.5. Alright, we've begun already in class to talk about logarithmic functions, and I want to continue that discussion here in this video for section 4.5, in which we plan to do this. We plan to learn the shape and the properties of the graph of a logarithmic function, just the beginning of section 4.5. Alright, and the way I'd like you to be able to know what the shape and the graph of a logarithmic function is I'd like you to be able to compare them with exponential functions that we've been studying earlier in this chapter. Alright, so looking at logarithmic functions as inverses is what we're going to do right here. And this will make sense to you in a moment. What I want you to do is show that y equals log base 2 of x is the inverse of y equals 2 to the x power. That will establish, hopefully, that there's a relationship between that of an exponential function and that of a logarithmic function that have the same base. And then we're going to compare the graphs, because once we establish that these two functions are inverses, we can use the graph of the exponential function that we know how to make in order to make the graph of a logarithmic function that we don't know how to make quite yet. Alright, well, first let's talk about how do you show that the logarithmic function is a function of that exponential function. Well, remember the way that you find inverses is that you switch the x and y values with one another. So take that equation, y equals 2 to the x, makes it x equals 2 to the y power. And then what we're going to do is we're going to solve that for y. Okay, now I want you to understand what we're saying here with this particular equation that we've got right there. We're saying that y is the power of 2 that gives me x. If I asked you guys what power of y gives you x, I would be asking you this question. What power of 2 gives you x? And the power of 2 that gives me x is y. Can you see how that is? If I make it 2 to the y power equals x, same thing that I've got right there. Alright, so exponential functions are inverses of logarithmic functions. Now let's compare their graphs. Alright, I'll give you a moment to copy all this down, or rather you should pause the video and copy the graph and then these two tables down, and then come back and listen to how I create the graph of each of these functions. Alright, now for exponential functions, we talked about how you can plug in anything you want to for the exponents of an exponential function. Alright, positive numbers, negative numbers, fractions, whatever, it doesn't really matter. And so what I'm going to do here is I'm going to pick three values to substitute in for x, and that y equals 2 to the x power, and what I'll do is pick a positive number, a negative number, and 0. So let's go -1, 0, and 1. And then we're just going to take turns plugging each of those numbers into the function. We can say then that 2 to the negative first power is 1/2. 2 to the 0 power is 1. And then 2 to the first power is 2. And so this graph looks like you would expect it to look like. Let's go ahead and plot those points. And then draw our exponential graphs curve. Alright, now remember some things about the graph of a logarithmic function. One of those things is that it has a horizontal asymptote, because there's no way you can raise a positive number to a power that's going to give you any negative values. Alright? Another thing is that we said as long as there's no vertical translation involved or so forth, that the y-intercept is going to be 0, 1. Okay, those are some properties that we know about about exponential functions. Now let's look at the graph of the logarithmic function y equals log base 2 of x. Now, we've already established that these two functions are inverses of one another. And whenever two things are inverses of one another, you can create the graph of one by switching the x and y coordinates of the other with one another. So, instead of graphing -1, 1/2, for the inverse we could graph 1/2, -1. and we could switch to other pairs of x and y coordinates as well, so that those are the points that we'd be graphing. Now, I'll tell you what, let me outline this in different colors so I can make this graph in a different color. Alright, so I'll make this graph in yellow. Like so. Alright, so just switching x and y coordinates around. Now remember, one other thing about the graphs of inverses is that they are reflections of one another in the line y equals x, which is just the line where all the x and y coordinates are equal to one another, right here. And you can imagine how those are mirror images of one another. Alright, now, because of some of the things we know are true about the graph of an exponential function, the horizontal asymptote, its y-intercept and everything, we can automatically know some things about the graph of a logarithmic function. For instance, if I reflect this, the horizontal asymptote, let's say, in that line y equals x, well, what it does is it gives you a vertical asymptote. The graph of a logarithmic function is going to have a vertical asymptote. And think about it. You can't plug in anything, or you can't find any powers of 2 that will give you a negative number, can you? So there's no way that x can be negative here. So you only have positive values of x. Alright, also, you're always going to have the point 1, 0 on the graph of a logarithmic function, assuming there's no translations or dilations, just like you always have the point 0, 1 on the graph of an exponential function in the same situation. Okay, anyway, let's take a look at some more practical things, but I wanted you to see what the graph of a logarithmic function looks like and how it's an inverse of an exponential function. Alright, some properties of the graphs of logarithmic functions. What we're going to do here is we're going to talk about what are the things that are true for a function y equals log base a of x, just a generic logarithmic function. We're going to make a little list here, so get ready. Alright, and the properties that we need to talk about will be domain, range, that kind of thing, vertical asymptotes, and so forth. Alright, now for the domain, what can you plug in for the index of a logarithm, basically? Well, we just talked about a moment ago how if you're going to have a positive number for a base, and you raise that to a positive power, it's guaranteed you're going to get a non-negative value right here. So it's impossible for x to be equal to anything that's negative, meaning that our domain is going to be x has to be greater than 0. Okay, remember you can write that in interval notation, 0 to infinity. Alright, I'm going to write the range in interval notation. And as for the range, hopefully you can visualize from the graph that this thing is going to go forever downward, and it's going to go forever upward. Right? It would keep going, angling off, up and to the right. Well, that implies that our output values, basically which are correspond with the exponents of our base, can be any real number. You can raise a to any power you want to and get some number x for it. So the range, we could say y could be all real numbers, or we can say that it includes everything from negative infinity to positive infinity. Alright, now back to that whole domain thing where we said x has to be a positive number. The fact that 0 is kind of the lower boundary for what you're able to plug into the function makes that line x equals 0, the y-axis, a vertical asymptote. So, have a vertical asymptote at the y-axis. And a couple other simple properties we're going to mention. Alright, and one of those we've already mentioned on the previous graph, the intercept, x-intercept, is always going to be 1, 0. And finally, unlike some other functions like parabolas, for instance, the graph of a logarithmic function is always increasing. So you increase the value of the index, guaranteed that the function's value is going to increase. Function is always increasing. Alright, so those are the properties of the graphs of logarithmic functions I need you to be aware of, we'll say. Okay, well, one last thing. I want to show you how you graph a logarithmic function. And we're going to graph y equals log of x. Now, I hope you notice here that within that logarithm, I didn't include a base. And that's because this logarithm is what's called a common logarithm. And what that means is this. If you don't see the base of a logarithm stated explicitly, then it's assumed that the base is a 10. And a base 10 logarithm is known as a common logarithm. Okay, so how do we sketch the graph of a logarithm? Well, quite simple actually. It's really about choosing input values so that we can easily evaluate the logarithm. All right? We're trying to figure out what power of 10 will give us some number of x, correct? So let's figure out numbers of x that we know happen to be powers of 10. Now here's some examples of numbers that are powers of 10. I'm going to write them in the xy table. 1/10 is a power of 10. 1 is a power of 10. 10 is a power of 10. 100 is a power of 10. All right, and as long as I choose things that are powers, input values that are powers of the base, it makes it very easy to evaluate, right? Whenever I try to plug in x, I'm trying to figure out what is log base 10 of 1/10. Well, the power of 10 that gives us 1/10 is -1. Whenever I plug in 1, I'm trying to figure out log base 10 of 1 equals what number? Well, what power of 10 gives you 1? 0. And so forth. 10 to the first power will give you 10. 10 to the second power will give you 100. Now this requires often that you change your intervals on your x-axis because we're going all the way from basically 0 to 100. We don't want to be doing that going by ones. I'm going to choose to go by, let's say, 20s. And then let's go ahead and graph the selected points. We said first of all when x is 1/10, y is -1. Well, 1/10 is going to be really, really close to the x-axis, correct? So there's that. We said when x is equal to 1 that y is equal to 0. Whoops, that would be really close to the y-axis as well. So let's put that there. We said when x is 10 that y is going to equal 1. And we said when x is 100, and you got 20, 40, 60, 80, 100, that y is equal to 2. That's going to be way out there. Remember that you have a vertical asymptote, so you don't want this graph to cross. Whoops, don't want to use that. We don't want this graph to cross the y-axis. We want it to start off really close to the y-axis, and then it kind of throws off quickly to the right, that way. Alright, that's how you graph a logarithmic function. You now know some properties of logarithmic functions. Let's put them to good use. Thanks for watching. See you next time.